So when I said at the beginning of the session on the applications of VR and AR on building projects by owners, designers, and builders, that my first experience dated back to 1995 in Pat Hanrahan's lab. The person I was working with, postdoc there, Bernd Fröhlich, was eventually, I think, one of the people you studied with. So there's a little bit of a connection to Gordon. But his talk will be broader than just AR, VR. Certainly relates to that, but I think and I think in that sense it builds very well on many of the cues you had and some of the comments you made. What you would like to show maybe next year is connection between AI and VR and generative modeling and so on. So I'm really excited that Gordon joined us here today, straight off a trip from the East Coast. So yeah, please take it away, Gordon.
Well, thank you for the introduction. It's great to be here. This is not normally my community, so I apologize if I present concepts that you might not be familiar with, so feel free to interrupt me anytime. I work at the intersection of computer graphics, 3D computer vision, and AI. So we think a lot about generative AI, how to not only generate content or reconstruct 3D content, but also how to put it on into immersive experiences. I sometimes like to start my talk by talking about this book, which I read many years ago, Snow Crash by the author Neal Stephenson. It's a pretty wacky story, so I don't know if you read it, but there were two concepts in there that were really interesting. So, by the way, this is the book that coined the term metaverse, if you're not familiar with that. But two concepts in there that were relevant probably to all of us. The first one is that the characters in this novel had these really advanced interfaces between their visual system and these virtual environments that allowed them to dive into the metaverse in a really immersive way. That was from the early 90s, and he was basically describing virtual reality, augmented reality as we know it, but in a really fully immersive way, such that the content was not distinguishable from reality for the user. The second aspect in there was the complex and lifelike virtual worlds that the characters would interact with. They were really indistinguishable from reality, and it wasn't entirely clear at the time, working in computer graphics, how you would actually create such environments. So interestingly now, 10, 20 years later, my group works on many of these topics. And back then I thought this would be a great research platform because it involves many different aspects that weren't figured out yet, including novel displays, applied vision science, computer graphics, 3D computer vision, but perhaps most importantly, generative AI. How do you generate these virtual environments? So my group has worked a lot on various display technologies, and I can't cover all of them in this talk. Basically, I'm going to skip this part because it might not be as relevant to you, but my group works a lot wearing my double E hat, electrical engineering. We build devices, display systems, imaging systems. I also co-founded 2 startups working on micro-LED light engines for AR displays. So I know quite a bit about the systems design of head-worn displays, but it might be a little bit beyond the scope of this project. So what I'd like to focus on is these emerging generative AI capabilities that allow you to do things like large-scale, dynamic, 3D generative AI. The reason why I'm showing this video is that PowerPoint suggested, for the first time in my life, something that was vaguely relevant to the content I was trying to put there when I entered the title. So in any case, how many of you are familiar with generative AI? Okay, so Martin just mentioned that you had some sessions already yesterday in this space, and you've probably heard of LLMs that generate text. But there are also generative AI systems that build on a slightly different mechanism, on diffusion models that are used to generate images. So text-to-image generation, like DALL-E from OpenAI, Stable Diffusion, or other methods, have become really popular in allowing you to take a text prompt and turn it into a high-resolution and high-fidelity image. Very recently, over the last few months, we've seen a lot of video models coming out. So you take a text prompt or single image, and you can generate a pretty lifelike video. We'll take a look at this in a second. Now, what I think about when I think about spatial generative AI is actually you want to have a 3D representation that you can navigate in, and that might be relevant to many of you. But you also want this to be dynamic, and ideally you want it to be large scale in the sense that it's not just constrained to a single object or a single person, but to complex environments. And so we can't do this today, but the community has made a lot of progress towards this, so I just want to sort of give you a quick snapshot of the state of the art in this domain. So currently, for various reasons that I'll go into later, it's not possible to generate very complicated, lifelike 3D dynamic scenes. It's a great research vision, and a lot of my community works on this space. But we're very close. So within the next year or two, we might just be there, if you look at the progress over the last year or two. So there are two potential directions that you can take to get to this large-scale 3D generation. The first one is you take one of these really new video generation models like OpenAI's Sora or Luma's Dream Machine, and you add camera control to that. So that means you can place a camera into the scene and you can freely move them in any way you want. So you could connect it to your head and use it in a VR setup where it's tracked, or you could just generally place it anywhere you want. The other way is to build a foundation model for 3D and 4D generation. And that's sort of like designing a foundation model from scratch. So I just want to tell you a little bit about our work in this general space. And I hope we have enough time for questions and answers and discussions after. Because this talk is a little bit targeted towards the computer science audience. So let's talk about video generation first. Many of you have probably seen these announcements from OpenAI. This model is called Sora. It's a video generation model. You can take a text prompt. The prompt is pretty small, so I don't know if you can read it, but it says something like a stylish woman walks down a Tokyo street, and so on and so forth. Very long and detailed description of the scene, but this video is generated with the model. It's not captured. It's not real. If you look at her legs, for example, you see some inconsistency, so it's not perfect, but it's getting pretty good. And this was like a jaw-dropping moment for the community where we felt like, okay, we're getting closer to the point where we're able to generate close to photorealistic video. Pretty long video too. Just before this, you could do maybe 16 frames or something like that at low resolution, which was not so realistic. So this was a big step in the community, and since then, this came out earlier this year, we've seen actually quite a bit of progress, and others have copied these types of models. It takes a small power plant and a few tens of thousands of GPUs and the whole internet scale video data to train this type of model, but it's possible. So now what's missing? To churn such a video model, which is not really controllable, you only have a text prompt to describe anything that's in the scene, right? So you have very limited control over this. In order to make this useful for a spatial generative AI application, what you first of all need is camera control. So that means you need to be able to place a camera into the scene and then freely move it. We've been working in this space and came up with a concept that we called camera control. It's basically a small network that adds on to an existing video model that can be trained. And we figured out sort of how to best condition the pre-trained video diffusion model to allow this camera control. It sounds a little bit trivial, but the problem is this. Once the video model is pre-trained, it takes many weeks, tens of thousands of GPUs, and lots of work to train this video foundation model. You don't want to touch it anymore, right? So especially in an academic context here, we have access to maybe a few tens of GPUs. We can't train this model. It's probably impossible to fine-tune it. Some of you might be able to do this, but we can't do it in an academic context anymore. So we need to be very careful about what types of projects we work on. So in this case, we work on these adapter networks that dock on to the existing foundation models. And so in this case, we figured out, okay, we're going to take the camera position and orientation, which is known as the extrinsic camera parameters, and we're also going to do a per pixel embedding of the ray parameter. So we encode every ray that is connected to one pixel and build this encoder network that is connected then to the temporal attention layers of the pre-trained foundation model. And this proved to be a pretty effective way in being able to directly control the camera. So what that means in practice is we can now take a pre-trained video model and we can specify a camera trajectory, and the video model behaves that way. So we can do text to 3D generation or text to video generation with a prescribed camera path. You can see a couple of examples here. A squirrel is eating pine nuts, so the video is being generated, but it also follows the specified camera trajectory. And you can see a couple of examples here. Now, we don't have access to OpenAI Sora model. This is closed and only accessible to very few customers of theirs, so we need to work with these open source models that are, provide far from the same quality as Sora, but the concept works, and likely you'll see things like that enabled for Sora or other video generation models soon. The other thing that you can do is take a single image, which you can always see in the lower left inset, and you can now extrapolate from that single image and generate a video with a prescribed camera path that extrapolates from that scene. So imagine you have maybe a picture of your construction site or of like some other location that you want, and you want to sort of move the camera around from there, but you don't actually have a full 3D model of the environment. The video model will give you a good preview tool that is plausible. It might not be physically realistic, but it's going to be plausible. So that's sort of like, in a nutshell, some of the work we've been doing on camera control for video models, and there will be many other types of adapter networks that allow you to control different aspects of this video generation process. Let me talk a little bit about 3D and 4D generation. This is a slightly different approach where we're trying to be clever. And clever in the sense that we don't want to use maybe tens of thousands of GPUs. We don't have the training data that we have for videos. Video data is abundant on the internet, YouTube, all these different sites, right? I mean, whether they allow you to use that data for training your model or not is a different question, but there is a lot of video data. There is not a lot of 3D data, and I'll get into that a little bit more later. So we need to be clever about how we design a 3D generation model, and we would typically do that by what we call building an inductive bias into the network. We force it to be 3D multi-view consistent. We force the data that we have to live in some kind of a 3D world. So this goes back to two essays that people wrote a little while ago. So there was one that's called The Bitter Lesson. Has anybody of you read The Bitter Lesson? Ever heard of this? Richard Sutton, it's a pretty famous thing. It's just one page long. And the basic summary, this was a famous researcher in AI who wrote a one-page article basically saying that all of our efforts in academia and industry where we're trying to be smart are going to be replaced by data-centric approaches. If we just have enough data and enough compute, we'll always be able to train networks that do better at some task than us trying to design an algorithm around it. So he was arguing that, and he gave many very compelling and convincing examples that, for image classification or any other task in computer vision, as soon as lots of data was available and lots of compute, people were able to outperform any other method that has been designed by the community before. So that's been the sort of the motto of OpenAI. OpenAI is following that approach. Lots of data, lots of compute, no cleverness, just brute force, and it works really well, right? There was another essay following up on this called A Better Lesson. Now, whether it's a better lesson or not is a different question, but that was arguing about we need to be smart. We need to build in the knowledge that we have into the model so that it's easier for the model to learn certain things. We don't need to learn things that we can model. We can put these inductive biases in there. And when I talk to an academic audience, they like that story because they can't train large models and they just can't handle it, right? So this is the only path they can do. And so we've been exploring this approach as well for 3D generation. This is a really fast-paced world. Some of these capabilities only came up over the last year or two. There's been a tremendous amount of development over the last 2 years on generative models, basically. All of this just came out over the last 2 years. Image generation, video generation, any 3D generation. We published a couple of influential papers in the space, for example, on the object level. So the idea here for this project, which we call GenVS, Generative Novel View Synthesis, was to take a single image of an object and then build a network around it that would allow you to move the camera around and extrapolate so that you can render the object from a different perspective. And we did that by designing a feature extractor that would extract features from this input image, lift those features into 3D, then you place a camera anywhere you want, you project the features into that novel camera space, and then you have a text-to-image generation or an image generation model. At the time, we didn't have any video models then, which was last year. Then have a 2D model that generates an image, again, from those reprojected features. And just by virtue of living in sort of a 3D space, these features would create this inductive bias and making everything a little bit more 3D multi-view consistent. That worked pretty well, and people got really excited about this idea of single image to 3D generation. We were able to demonstrate results like this, trained on real data, like fire hydrants. Our method is on the right. We can now create a plausible camera path around this object, whereas previous approaches, again, last year, were totally failing. And this is a really ill-posed inverse problem, because taking a picture of an object like this remote control, it doesn't tell you anything about how it looks from the other side. But as humans, we have a built-in prior. We probably think, oh, this must be a box. The color probably extends. We have a built-in prior, and we can sort of hallucinate what might be there. But there are many different solutions that are equally plausible. So the generative model will give us the most likely solution that was there, that's still consistent with the constraint of the input, whereas previous models would try to sort of average out over all the possible solutions. So this works for room scale scenes too. In this case, the input image is on the left. It's trained on a data set called Matterport 3D. It's like basically a bunch of real estate data that was scanned from indoor scenes. And our results are in the middle. We can now move the camera around and generate plausible indoor scenarios. They're not realistic, they're not correct. If you look at the reference on the right, they don't resemble exactly the ground truth, because it's an ill-posed problem. We don't know what's really there, but it is able to generate something that looks plausible as trained by the data set, whereas previous methods didn't do that. So these are emerging capabilities of not just our work, but also the community at large, capabilities that you might be able to use pretty soon. This was a project, so I'm just going to give you an overview of a couple of capabilities now that you'll see coming up soon, because those are sort of like all published around now, and these are specifically from our group. We've been trying to be clever about, if you know more about the type of object that you want to generate, then you can be clever. For example, in this case, we wanted to generate humans. And for humans, we have template shapes that sort of look like a proto-human if you want, but they don't look like any human in specifically. But we can animate this proto-human. It's called a parametric model of a human, called a simple parametric representation. Now we can use text-to-image generation models, use a text prompt to generate an image, and then we can extract the useful features from the generative model, attach it to the 3D template that we have, and animate it with the template, and then reproject it into 3D, into the novel views. So what this allows us to do is, without having access to a video model, we can still animate things, we can still reproject things into novel perspectives or body poses, without actually having to have a full-blown video model. And we can edit things and make it sort of as good as the underlying base model is. So all of these are based on foundation models, so the quality that you'll see will be sort of limited by the foundation model itself. So imagine you have a house, and the house is most likely close to a box or something like that. You generate one perspective, or you render one with your Autodesk program or something like that. Instead of rendering many different perspectives and waiting for a long time, you could just reproject this single perspective onto the box, move the camera around the box, and reproject it to get fairly plausible extrapolation capabilities. 3D generation is really hard, so people have come up with a two-stage approach, and this is sort of like the default by now in industry. Is the first stage is to actually take a text prompt or a single image and generate just a few views, so a sparse set of views of the underlying 3D scene. For example, the first approach is called Instant 3D, was published by Adobe last year, and they take a text prompt and generate 4 images of a corresponding scene. It's not perfectly multi-view consistent. So you can't just take your standard structure for motion or a 3D reconstruction program and reconstruct the scene because A, there aren't enough views. CoMap or other structure for motion methods need many, many, many different views. So it's too few views, and these views are also not perfectly consistent. So even if you had a lot of views, it'd be very challenging to reconstruct anything. Similarly, other research groups like Stability AI and others have introduced single image to sparse view generation approaches, and that's great. But if we want to actually get a 3D model from this, we need to come up with some way to take these sparse views and reconstruct a dense 3D scene. We've worked on this, and we called our model Gaussian Reconstruction Model, GRM, and it does exactly what I described. It doesn't only do it well, but it also does it really fast. Within less than a second, it can take these few views and reconstruct a full 3D scene. So what that allows us to do is, again, what I mentioned before, text to 3D, so you can give it like a text prompt, like a cat wearing eyeglasses, and it will generate a cat wearing eyeglasses. So these are objects that have never been seen in the training data. The generative model itself has the compositional capabilities where it can learn different concepts from different content and put them together in a sort of meaningful way. You can do single image to 3D reconstruction. Again, this is an ill-posed problem, and really only generative methods can give you something that looks plausible for the parts of the scene that have never been seen in this case. And you can also do multi-view image to 3D reconstruction, so if you have just a few sparse views of the scene, you can actually get a pretty decent reconstruction. And this is important whenever you want 3D reconstruction, but you don't have enough input data to run multi-view stereo or structure for motion. The key here was an innovation in the network design, or basically in the representation of the scene. So we're using a transformer architecture, and I don't want to go too much into the detail, but think about all the middle part is a black box that is a specifically designed transformer, which is a network architecture, and the input are the 4 images, and it translates these input images from RGB per pixel to a 3D Gaussian representation. So instead of having RGB value for each pixel, we now have a couple of attributes that include 3D position, orientation, color, and other attributes of a 3D blob, if you want. 1 blob per pixel. And because they live in 3D, we can reproject them into 3D and then render them from arbitrary perspectives. So that's sort of the high-level idea of this specific sparse view reconstructor. It works mainly for individual objects, and I'll tell you in a second why. But you can apply it to more complex scenes by segmenting out individual objects and applying it to these specific objects. So then you do basically a single image to 3D reconstruction or generation approach. Works pretty well for many types of objects. So here's a challenge for this community. We don't have enough training data. Training data is too limited. For training image data, we have almost unlimited images on the internet. All of these text-to-image generation models that you can find online, like DALL-E and so on, they're trained typically on a data set called Lion 5B. So we have 5 billion images that these models are trained on. And it's hard to imagine what type of content was not seen within these 5 billion images. Probably anything that you can come up with, right? So it's a lot of data. This is the largest 3D data set that's publicly available, and it's propelled the community forward, but it's only 10 million views. So we have orders of magnitude less training data. And these are all computer-generated assets, so they don't even look super realistic. So any 3D generative model that we're going to build on this data is going to be limited to the quality and the diversity of this training data. It's really challenging. So a couple of questions are, can we leverage 2D image data to train 3D models? Can we, somehow, how do we get to this large-scale 3D generation? There are a few data sets emerging, but they're even just like 10,000 data sets or images or scenes. So it's even orders of magnitude less. We've worked on both of these directions, basically trying to use 2D data to train a 3D model. We've been developing neural representations of 3D scenes that would allow us to use 2D generation methods, lift them up into 3D, and then reproject them with really efficient representations for the scenes. And that allowed us to train, for example, faces. So these are a couple of identities that we're able to generate from a training data set of just faces. So this is object specific, but none of these people exist. We only have single views of each one person, any one person, but the model is actually pretty good at generating close to photorealistic characters. It inherently learns some amount of 3D representation, even though we don't have any 3D information for any of the training images, simply because the model understands that it needs to learn some kind of underlying 3D scaffold that allows it to, move the camera around in a consistent way. Works for cats, works for any other object really too. And this is probably my favorite example because it shows that the model itself, you can basically, it represents any one person by a number, which we call a latent. And if you interpolate these numbers representing different identities, then you're going to always get some identity that looks sort of plausible as an identity, right? But none of these people, again, exists, but it learned a continuous space representing human heads, basically. We looked into allowing more control for this. For example, relighting. Can we learn this in a way that we can later specify not only the camera position explicitly, but also the lighting? So in this case, you're seeing moving cameras, interpolating characters, and now we're specifically constraining the lighting situation using an environment map that you see on the bottom. So daylight, nighttime, whatever, indoor scene, and we're rotating that around. So it gives us more control. The fact is that individual objects like faces are fairly easy to learn because most of us look pretty similar. We have 2 eyes, a nose, a mouth, 2 ears. So it's sort of easy to align different heads. And yes, there's a lot of individual variation, but that variation is actually pretty small compared to, for example, full bodies. If you look at publicly available data sets of full body humans, there's a lot of diversity. People have accessories like purses, they have all kinds of different body poses, they ride bikes and tricycles and segways and all sorts of other vehicles. So it's really challenging to align them into like a sort of a canonical frame. We came up with some strategies for doing that, specifically for humans, because we have these parametric representations for humans. And we learn 3D generative models to generate different identities that we can now generate, we can interpolate, we can make them move in any way we want, basically. So from a static image data set, we can learn to generate these avatars, and we can explicitly control their body motion. So this was a new capability that people hadn't seen before. Works okay, not quite photorealistic at high resolution, but it's getting there. Okay, so one last project that actually shows a first path towards large-scale 3D generation. This was a project we did in collaboration with Google. One of my students was doing an internship at Google last summer, and he got access to all the Street View data. And what we thought we're going to do with it is train a large-scale video generation model with camera control, like the one I showed you in the very beginning. But it's conditioned by a map. So in this case, we have a map, like from Google Maps. For each pixel on the map, we have a height value. So this gives us like a box-like representation of the buildings. And then we trained this camera controllable video model on this. Now we have large-scale data. And works pretty well. We call this streetscapes. It works so well that we can actually run our favorite 3D reconstruction method on top of the generated video to get perfectly multi-view consistent data. So the generated video has a little bit of flicker still in it, but the generated video is then pretty good. So I don't want to go too much into the technical details, but this is basically a mix of 3D generation and video generation again. You can see 4 different maps here. You can see sort of where the camera is looking at. We render a couple of proxy information into this G buffer. So this is like basically the box-like representation of the buildings. It's like a proxy geometry. And then in the middle, you can see the generated video, which still has a little bit of flicker. But then we can do a 3D reconstruction from this densely generated data and get a perfectly 3D reconstructed scene. So you can probably appreciate this better in the zoom in. Again, this is sort of like what Street View might look like in the future. So these buildings are not reconstructed. They're fully generated from scratch, but learned on lots of real street data. As you might know, a street view is not, so these street view cars drive around the streets, they take an image every 5 seconds. So what you get from street view today is like this weird interpolation where you can interpolate from one view to another. So this allows us to get very smooth interpolation capabilities using the pre-trained generative model, but we can fully manipulate the scene. We can change the time of day, we can change the style of the street, we can change the weather condition. For example, we trained this on a couple of cities, Paris, London, Manhattan, and Barcelona. So we can, with text input, change the weather in Barcelona to be snowy, which you wouldn't normally see, because the model learned the snow from Manhattan. We can also make, create a rainy day. We can change the time of day. We can basically change anything you want. It looks pretty plausible, but it's fully editable using text prompts. We can take the same map, and this is a map of Paris, and make it look like Paris, but we can take the same map and make it look like Barcelona or New York City or London, because the model has learned the style of each city and what makes the city look like that city. So it's sort of decoupled. Compared to methods that have been out there just before, like Infinicity on the top, these video generation models provide really new capabilities that are a big step forward in this community. If you're interested in this general space, I wrote a review paper also on diffusion models. And I'm going to skip the last project because it's not as relevant, but just wanted to tell you a little bit more about my group. We work on AR, VR devices, new types of cameras, neural scene representations, rendering, generation, so lots of 3D computer graphics, 3D computer vision AI, and also a little bit of Gen AI for other types of applications like proteins. Thanks for your attention. I hope we have some time for Q&A, and yeah, thanks again for the invite.
Yeah. Thanks, Gordon. Yes, we do have time for quite a bit of time for Q&A. And yeah, so for Gordon's benefit, say the name and company. Yeah.
Hi, Gordon. Henning Rodell with Hard Hat Robotics. With diffusion type AI, right, and learning, what are some of the sort of broad stroke limitations? Like where does the model tend to fail, or that technique rather tend to fail versus get things represented accurately?
Okay, great question. So just to maybe take a step back, I would say in our world we think about two different generative AI approaches right now. One are these autoregressive models that are being used by LLMs, multimodal LLMs like GPT and so on. But these haven't been shown to be as good for pixel level generation, images, videos, that kind of stuff. So for those methods, we currently use diffusion models, two different classes. Eventually they might converge somehow, but that's not the case yet. So where do diffusion models fail today is the question. It's sort of hard to say. So first of all, they're pretty compute intensive. So you can't, even once the model is trained, it takes a little while to actually generate something. So even at inference time, making them efficient is actually a challenge. The previous generation of generative models, generative adversarial networks, they were really fast at runtime, but these ones are slow. So that's a limitation. The second limitation is, again, they're very data hungry. They need a lot of data. So again, for images, it works really well. Very recently, people have shown that for video, it works really well. But all of these 3D generation tasks I showed you, they are very first steps towards making this really useful. And I think that's a big challenge. And it's sort of like a chicken and egg problem because A, we don't have large-scale 3D training data, and B, even if we did, we wouldn't really know exactly how to set this up because these models are so hungry for resources, memory, compute. So 2D is okay. 3D is already very challenging. Now, if you want to do 4D generation or even just 3D scene level generation, it would be challenging to do that on current generation GPUs. You'd need lots of compute power. So not quite clear exactly how to do it. That's why I think people always try to use the latest and greatest model and somehow hack it by taking a 2D generation model and sort of hacking it to be able to do something in 3D or something in video, but it just hasn't shown the same quality, because if you take a 2D model and you want to generate a video, you get flicker, because the model doesn't understand that, it doesn't understand anything about motion in the scene. It just, on the frame level, it looks great, but the transition between frames aren't great. So now you can train a video model and you can get rid of that, but that comes at an enormous compute cost. And the data is also different, right? So similarly, now you can use, you can build 3D generation models on video generation models with this camera control. They will look great as videos, but they might not adhere exactly to the camera perspective that you specify. So they might just be a little bit off. So if you wanted to do a 3D reconstruction, might not work well because the camera poses might not be actually accurate. It'll try to do something like the camera path, but it's not going to be super accurate. So for CAD applications where you need, or robotics, you said you work on robotics, right? If I have a robot that needs to grasp something, it needs to be pretty accurate, I assume, right? So the video generation route for 3D is maybe good for visual effects and where things need to look plausible but not need to be super accurate. So for accuracy, then you really need to, I think, have a model that is trained on 3D data. And then it's really challenging to extend a 2D or a video model to generate something that's 3D consistent. But again, then we don't have the training data. We don't know exactly how to represent the 3D scene. It's, challenging. But this community is very active. Whatever we think is, this is the next big challenge, for the next conference deadline, I'm going to promise that there will be 10, 20, 50 paper submissions on archive on exactly that. And the next conference deadline is going to be end of this month, and then there's going to be another one in mid-November. So my guess is that we'll see a lot more video stuff now in the research community because it's already been shown by OpenAI to be there. So people will do lots of video stuff. And then we're probably going to see some big improvements in 3D also very soon. So I think if you're interested in 3D generation, I think over the next year, a lot of things will move in this space. And maybe you ask, why do I need video generation? You probably have a specific CAD model, you have your architecture program, you have everything is modeled already. Think about these as foundation models, right? What is a foundation model? A foundation model is something that's pre-trained on a huge amount of data, and what it learned in that pre-training stage is reasoning capabilities. It's seen all the buildings you can see, and now it can do interesting things later. It can help complete new parts, it can hallucinate things, it can assist the designer in doing stuff, it can, help you with any other tasks that comes after. The notion of a foundation model is that it provides a foundation for many other verticals building on top, and you don't need as much training data for this, fine-tuning for the second stage. You just need your personal client's data perhaps to fine-tune it on that. And I think that's a real promise for any of these foundation models.
Michał Wojtak with Mortenson. So from what I've seen, and if I understand that's complex topics, the models that are being generated are basically generated on a frame-by-frame basis. So basically there is no relationship between them. So you can kind of like extract the complete model of the city, for example, right? You just see the kind of snippets of it, right? But in the more practical applications for AEC industry, right? Is there any research being done into how to train the AI to reconstruct, for example, point cloud data from different laser scans, right? To make it more optimized, less power hungry, so we actually can have a reconstructed 3D model that we can use later on in a CAD application.
Oh, absolutely. This is a great question. So can we use this to, process sparse point clouds, incomplete scans, things like that? That's exactly this foundation model idea that I mentioned. Like once you have, let's say, a 3D foundation model, you can use it as a prior to fill in missing parts. And this is basically the same idea as this single image to 3D generation, as you have some constraints given by the input. Could be a single image, could be a sparse LiDAR scan, could be a couple of images and some LiDAR scans. It could be a dense LiDAR scan too. The model will help you fill in the parts in between with reasonable things because it learned this reasoning capability in the pre-training stage. And that's very different from reconstruction. So for example, when you look at LiDAR data for cars, it's sort of limited to a certain range, vertical range. But if you have a pretty decent idea of how structures look like in general, then you can extrapolate beyond that. And in fact, Adobe has already started to roll out some of these generative AI capabilities in Photoshop and 2D imaging processing tools. And I think their most used feature is generative fill. So take a region that is not there and fill it in with something that looks reasonable. People use that. It's really hard to do manually or with existing techniques. Or extrapolation. You take an image that is a certain aspect ratio and you want it in a different aspect ratio. So there's vertical or horizontal bars on the rest of the image. You can fill that in with very meaningfully looking content. You can imagine the same thing in 3D. Given partial data, given noisy measurements from a scan, maybe you had a car going by or you have limited angles at which you can scan your buildings. You can fill in the rest with something that looks very reasonable. So that's exactly the idea of these foundation models, is fill in the rest. Just on your earlier comment, so the city scale generation was sort of a video model that generates 4 frames at a time. So it doesn't generate the whole city scale scene. It generates the next 4 frames in an autoregressive way. So it'll keep generating the next 4 frames, frame by frame. So there is some consistency baked in, but it is sort of limited also because the training data is not videos. It's these choppy images. So there was never, the training data has never seen a flicker-free thing because you only have these sparsely sampled images. So the capabilities of the model will be limited by the model itself, but also by the training data to some extent. And then what we did to reconstruct the scene is we generated all these frames and then we used traditional 3D reconstruction, which worked okay. It's challenging for leaves and very small details. There it gets a little bit blurry, but for buildings and even some of the cars and things like that, it worked pretty well, but it's very improvable, yeah.
Alberto Tono, PhD with Martin Fisher. I'm wondering if you have any insights regarding smarter architecture, like you were using transformers. Is there any new architecture or new direction that, as a researcher, we should look into it?
Yeah, okay, great question. So a transformer is the standard neural network architecture being used for large-scale models today, for LLMs and anything else, really, right? It's like not a fully connected network, it's not a CNN, it's a specific architecture that has really changed the game in AI. And the benefit of a transformer is that it is very scalable to huge amounts of data, to many GPUs. You don't have to, you don't have to do anything special. Once you have your transformer set up, it works well for certain types, small data sets. It works well for very large data sets. The only thing you really need is figure out how large you want your model to be for the specific training data you have. So if you read, for example, the Llama 3 paper or papers like that, they will do a lot of, test runs of the model to see how it scales and then determine based on the amount of training data that I have, how large does my transformer have to be? And that's pretty much all you need to figure out. And then you need, tens of thousands of GPUs and scale the whole thing up. So transformers have demonstrated the scalability. No other network architecture has shown that. So are the transformers the best? Maybe, who knows, but they are the only ones that have been demonstrated to be scalable. So if you follow the bitter lesson and you want to follow this data-centric approach and you just want to scale it up with brute force, transformers are pretty much the only architecture that you can use. As soon as you're trying to be clever, people who work on the scalable approach will tell you that anytime you put an inductive bias on it, will hinder the training, it's not going to work on large-scale data and so on. But this is where small-scale data might be useful because transformers might not scale to small-scale data. They might not do anything meaningful if you don't have enough data. And then you need to be clever. And there is the Wild West of how to represent the 3D scene, how to train your model. That's an active area of research, I would say. But for image and video generation models, transformers are a way to go because we have a lot of data and we have these scalable architectures. Yeah.
I'm Zahra Mazlagani, Martin's PhD student. I have a question. I'm wondering if you had any computational cost problem. If so, how did you fix it? I'm wondering if you used the high-performance computing to address it, or did you use GPU acceleration for this problem?
Yeah. So the question is about computational budget, right? So I would say compute is, NVIDIA was the world's most valuable company for a short amount of time for a reason, because they produce the GPUs that everybody uses to train these models, and it's not, like, you imagine this, like these GPUs that are used to train the LLMs, H100s specifically, they cost $40,000 per piece, more than my car, much more than my car, because I have an old car, but probably more than some of your cars too. And you need tens of thousands of these GPUs to train a model once. Now, that doesn't even include any of the pre-training, hyperparameter tuning, whatever, right? Or, so you need a power plant to power that. Like, this is a whole ecosystem of people snatching up power resources, building these data centers with massive amounts of GPUs in there. I mean, we can't compete with that in academia. This is for a few really well-funded companies like OpenAI, Google, Meta, a few others, right? I mean, in academia, we don't have access to these resources. I have 3 servers in the lab with 10 GPUs each, so, you know, and that's shared by maybe 15 students, right? So on average, you get 1 GPU or 1.5 GPUs. So how are you successful? So, I mean, we've been a little bit opportunistic in collaborating with the industry quite a bit. So we've collaborated with NVIDIA, Google, Meta, others, and sometimes we get access to their clouds. So if students do internships there, you know, they work on a project there, maybe sometimes we continue the project, we continue getting access to the GPU resources. So that's been one strategy. Stanford has a relationship with Google also, so we can apply for these projects and get GCP credits, so cloud credits. It's not a huge amount, but it helps. And then, yeah, I don't know, being opportunistic and resourceful in leveraging your connections to other institutions or companies that have a lot of GPUs has been very helpful. Yeah, I don't know. It's a war for GPU resources. I mean, we lose PhD students who are admitted to Stanford who don't come here because we don't have enough GPUs. They say, hey, first question is, how many GPUs do I get when I join your lab? If I tell them any number that's below, you know, double-digit number, they might just go somewhere else or stay in industry or whatever. It's a really different time from when I did my PhD. Yeah.
So I'm curious whether the science scenario that I have in mind is realistic or even too mundane for what you showed. I was looking at street view generated in New York, Barcelona, and so on. I thought, okay, this could have been helpful when I was working with Walt Disney Imagineering on the design of Disney's California Adventure. And it took a long time to come up with a design where the Imagineers felt there is enough theming here. The scenes are constructed well. This works for a 5-year-old boy. This works for an 80-year-old grandma. This works for a family with 12 children. This works for, a teenage couple. I mean, many different situations that they wanted to explore. And I thought, okay, if we could just generate a whole bunch of scenes, video experiences, realistic, not exactly what it's going to be, and have a kind of a multi-camera approach where, you're a 3-year-old, this camera is a 3-year-old walking through, this is a, older person, it's a family, etc., and you have an idea what they kind of care about. I think we could have come up with parameters for the design more quickly than we did at the time, taking months to come up with what works. I don't know, is that...
Yeah, potentially. So I would say...
Am I far away from...
No. This is great. So, I think these types of tools can help in different stages of the design process. They can help generate sketches, like just early conceptual sketches. Text-to-image generation models are pretty good at that, right? Like think about fashion designs or building designs or things like that. They can do the sketches. They can do colorful sketches. They can do photorealistic renderings. That you don't need to actually render anything to get a full 3D perspective rendering of something. You can change the lighting. How's it going to look like if the sun is over here, if it's over here, right? If you have camera control, you can place the camera at different eye levels, as you said. Very interesting, potentially. You can sort of generate a lot of the previews right now. And, are we Is that good enough for like the CAD rendering and the CAD modeling yet? I don't think we're quite there yet. But I think that's certainly on the horizon in the next, I mean, I would say decade, but then this field is moving so fast that I'm sure we're going to see interesting things happening over the next few years or even months. I don't know, right? So right now we're in the prototyping stage. Image generation is figured out. It's basically a solved topic, I would almost say. Like there was a recent release of a model called Flux. Works really well. I think it's going to be very hard to beat that. Video generation is already there, but we don't have access to the models yet. It's behind closed doors at OpenAI and a few other companies. I'm pretty sure we're going to see these models mature and be accessible also soon. I think 3D is still a big frontier for the next little while at least. That's what I tell my students to work on, basically.
Great. Thanks a lot, Gordon, for sharing super exciting work from your lab and giving us a glimpse into the future. And we can reflect on what it means for our industry in terms of what we can do how quickly, how well, what kind of expertise people should have, and so forth. But thanks for opening our eyes to that. And let's have a hand of applause for Gordon.
Thank you.